granite is harder than bronze. The Great Pyramid contains thousands of tons of precisely cut granite. The accepted construction window is roughly 2 decades. Those 3 statements coexist in textbooks without tension. And yet, placed side by side, they form a measurable question that demands arithmetic rather than admiration. What engineering fact does not align with assumed capability? On the Giza Plateau, the structure attributed to Khufu rises from limestone bedrock in geometric stillness. Its core is largely limestone. But deep within it, in the King's Chamber, in the relieving chambers above, in portcullis systems and structural beams, lies granite, not decorative veneer, structural mass, precision-cut stone hauled from Aswan, nearly 800 kilometers to the south. Granite is not cooperative material, it is an igneous rock formed under immense pressure, composed primarily of quartz, feldspar, and mica. Quartz, its dominant crystalline phase, ranks at 7 on the Mohs hardness scale. Feldspar falls around 6. Copper, by comparison, sits near 3. Early arsenical bronze does not rise dramatically beyond that range. In simple terms, the cutting medium available in Old Kingdom Egypt was significantly softer than the material it was shaping. Hardness alone does not make cutting impossible. Abrasive techniques allow a softer carrier tool to move harder particles across a surface. Egyptian stoneworkers are believed to have used copper saws and tubular drills in combination with quartz sand slurry. In this system, the copper does not cut in the modern sense. It applies pressure and motion. The quartz sand performs the abrasion. Dolerite pounding stones, harder than granite, were likely used for rough shaping at the quarry face. The accepted historical framework situates the construction of the Great Pyramid within the reign of Khufu, traditionally estimated at approximately 23 to 27 years during the 4th dynasty. Workforce estimates vary. Archaeological evidence from worker villages suggests a rotating labor force that may have ranged from 20,000 to 40,000 individuals during peak periods, though not all would have been stone cutters. Many were haulers, food producers, administrators, and support staff. The number directly engaged in granite extraction and finishing would have been a subset of the total. The contradiction does not emerge from doubt that Egyptians built the pyramid. The material culture, quarry marks, settlement remains, and administrative inscriptions support Old Kingdom authorship. Nor does the contradiction arise from disbelief in ancient ingenuity. The question is narrower. It concerns rates. If granite removal proceeds at a certain measurable speed per hour, and if the pyramid contains a certain measurable volume of shaped granite, then the total labor hours required can be estimated. If those hours exceed what a realistic workforce could provide within 2 decades, then the assumed capability must be reassessed, not emotionally, but numerically. This is the cutting speed problem. Granite does not yield quickly. Modern experimental archaeology, using reconstructed copper tools and abrasive slurry, has demonstrated that material removal rates are slow, soaring advances by millimeters per hour under sustained effort. Tubular drilling progresses gradually, producing distinctive spiral striations consistent with abrasive action. Copper edges deform and must be rehardened or recast. Sand must be replenished. Pressure must be constant. The work is physically demanding and repetitive. Now scale that to architectural quantities. The granite inside the Great Pyramid is not symbolic token stone. The King's Chamber alone is constructed entirely of massive granite blocks, including beams weighing between 40 and 70 tons in the relieving chambers above. Portcullis slabs in the ascending passages are likewise granite. The cumulative granite mass is often estimated at roughly 8,000 tons. Converted into cubic meters, that represents thousands of cubic meters of stone, requiring extraction, shaping, transport, and finishing. Each cubic meter must be detached from bedrock at Aswan, roughly squared, transported downriver during navigable flood seasons, hauled up the Giza Plateau, and then precisely shaped for structural integration. Every stage consumes time. Every stage consumes energy. But the shaping stage, the reduction of raw granite into dimensionally controlled architectural elements, is where hardness meets arithmetic. If a copper saw using quartz abrasive removes perhaps a few cubic centimeters per minute under ideal conditions, the hourly removal rate can be expressed. Multiply that by daily working hours, multiply that by number of workers assigned specifically to granite shaping, multiply that by years available. The result must at least equal the total granite volume incorporated in the pyramid. And here the unease begins. Because removal rates derived from experiment are not theoretical abstractions, they are measurable. And when those rates are conservatively scaled against thousands of cubic meters, the required man-hours accumulate rapidly, not impossibly, but uncomfortably close to the limits imposed by a finite rain. This is not an argument from incredulity, it is a matter of throughput. If the granite cutting stage consumes disproportionate labor time relative to limestone block production, then it becomes a potential bottleneck in the overall construction sequence. Large projects are governed not by average speed, but by the slowest critical process. If granite shaping is slow, it defines the tempo of internal chamber completion. The commonly cited construction window of roughly 2 decades assumes continuous seasonal labor, efficient coordination, and stable political authority. Agricultural cycles would have limited full labor mobilization to Nile inundation months, when fields were submerged and farmers available. Outside flood seasons, workforce size likely contracted. Therefore, annual effective working days must be realistically estimated rather than idealized. When granite hardness of 6 to 7 on the Mohs scale meets copper hardness near 3, the disparity is not mystical, it is physical. Abrasive systems can bridge that disparity, but at calculable cost in time and tool wear. Copper tools deform quickly under quartz abrasion. They require frequent reshaping and resmelting. Copper itself had to be mined, transported, smelted, and distributed. Each of those steps imposes its own logistical demand, so the question stabilizes into a clear form. Given granite hardness and composition, bronze and copper material limits, abrasive sand mechanics, estimated granite volume inside the pyramid, a construction window of approximately 23 to 27 years, and a workforce that includes but does not consist entirely of skilled stoneworkers. Does the measured rate of granite removal align with the available labor hours? Or does the arithmetic compress the timeline beyond comfortable plausibility? The answer cannot be assumed. It must be calculated. And before that calculation can be responsibly attempted, one foundational quantity must be established with precision, the exact amount of granite that required shaping. Because in any engineering audit, volume precedes velocity. Granite is not a single substance. It is a composite born in fire, an intrusive igneous rock crystallized slowly beneath Earth's crust. Its strength is not uniform. It is the product of interlocking minerals formed under immense pressure and geological time. In the granite used within the Great Pyramid at Great Pyramid of Giza, 3 primary minerals dominate: quartz, feldspar, and mica. Quartz forms the hardest fraction. On the Mohs scale, it ranks at 7. It resists scratching from nearly all common metals. Its crystalline structure is rigid, brittle, and chemically stable. Feldspar, slightly softer at approximately 6 on the Mohs scale, provides bulk volume and structural cohesion. Mica, present in smaller quantities, forms thin, sheet-like inclusions, contributing less to hardness but affecting fracture behavior. This is not soft sedimentary limestone. Granite is granular, crystalline, and mechanically stubborn. Measured compressive strength of granite ranges from approximately 130 to 250 megapascals, depending on composition and microstructure. To place that in perspective, this is comparable to modern structural concrete and significantly higher than most ancient construction stones. When loaded in compression, granite resists deformation extremely well. But cutting is not compression. It is fracture. Fracture toughness quantifies a material's resistance to crack propagation. Granite's fracture toughness typically lies between 0.8 and 1.5 megapascals square root of meters. That value reflects its brittle nature. Once a crack initiates, it can propagate along grain boundaries. This brittleness allows pounding techniques to detach blocks, but controlled shaping requires sustained abrasive action rather than brute impact. Abrasion resistance is critical here. Quartz crystals embedded within the granite matrix act like microscopic blades against any softer material brought into contact. When a copper tool slides across granite, the quartz grains abrade the copper rather than the reverse. Therefore, direct cutting by copper alone is mechanically implausible. Only through the introduction of harder abrasive particles, such as quartz sand, can effective material removal occur. Energy is required to fracture granite. While precise values depend on fracture mode and tool geometry, laboratory measurements suggest that removing 1 cubic meter of granite through mechanical fragmentation requires on the order of tens to hundreds of megajoules of energy. Even if we adopt a conservative lower bound estimate, say 50 megajoules per cubic meter, the energy requirement remains substantial. Now we turn from properties to quantities. Inside the Great Pyramid, granite appears selectively but strategically. The most famous concentration lies in the King's Chamber. This chamber is constructed entirely from large, precisely shaped granite blocks, forming the walls, floor, and ceiling. Above it are 5 superimposed relieving chambers, each separated by massive granite beams designed to redistribute vertical load away from the chamber ceiling. Those beams are immense. Individual blocks weigh between 40 and 70 tons. Their placement more than 40 meters above the base demands not only lifting capability but prior shaping accuracy. Granite also forms the portcullis system in the ascending passages, heavy sliding slabs intended as blocking devices. These are not rough quarry stones. They are dimensionally controlled components designed to fit within constrained passageways. Estimates of total granite mass incorporated into the pyramid commonly exceed 8,000 tons. Some calculations place it closer to 8,500 tons, depending on inclusion criteria. For our purposes, 8,000 tons serves as a conservative baseline. Mass alone is insufficient for cutting calculations. Volume determines removal time. Granite density averages approximately 2,700 kilograms per cubic meter. Dividing 8,000 metric tons, 8 million kilograms, by 2,700 kilograms per cubic meter yields roughly 2,960 cubic meters of granite, nearly 3,000 cubic meters. That is the volume that must be detached from bedrock, shaped, and finished. To visualize this, a single cubic meter of granite weighs 2.7 tons. The granite within the pyramid corresponds to approximately 1,100 such blocks of 1 cubic meter each. In reality, block sizes vary, some much larger, some smaller, but the aggregate volume remains near this figure. 3,000 cubic meters may not appear overwhelming in modern industrial terms. A contemporary quarry with diamond wire saws and diesel equipment could remove such volume in weeks. But industrial tooling operates with steel alloys harder than quartz, driven by kilowatt-scale motors. Old Kingdom Egypt did not possess hardened steel. It possessed copper, arsenical copper, early bronze, dolerite pounding stones, and abrasive sand. The granite itself was quarried at Aswan, nearly 800 kilometers south of Giza along the Nile. The Aswan quarries still preserve unfinished obelisks and extraction scars that testify to large-scale granite work during pharaonic periods. Extraction at Aswan likely involved pounding with dolerite balls to carve trenches around intended blocks, followed by controlled detachment. Even before shaping, the granite had to be separated from mother rock. Each trench carved into quarry bedrock represents hours of repeated impact. The unfinished obelisk at Aswan illustrates the scale of such labor. A single monolithic piece partially detached but abandoned due to a fracture. Once freed, granite blocks had to be roughly shaped at the quarry, transported downriver during Nile flood seasons, offloaded near Giza, and hauled to the plateau. Only then could final shaping and fitting occur. Every cubic meter of granite inside the pyramid thus represents energy expended in quarry detachment, labor expended in rough shaping, river transport time constrained by seasonal hydrology, hauling force applied across desert terrain, and fine finishing work within the construction site. But the cutting speed problem isolates one variable above all others: the rate at which granite could be shaped using available tools. If 3,000 cubic meters required surface finishing, squaring, leveling, joint matching, then the total surface area worked may exceed simple volumetric estimates. A block does not require removal of its entire volume, only the outer geometry must be shaped. Yet the amount removed during squaring and smoothing remains measurable. Even modest surface reductions accumulate. Removing just 2 centimeters from each face of a 1 cubic meter block equates to roughly 0.12 cubic meters of material removed. Multiply that by hundreds of blocks and removal volume rises significantly. Thus, the question grows sharper. 3,000 cubic meters of granite exist within the pyramid. Perhaps a fraction of that volume was removed as waste during shaping. The remainder was preserved as structural mass. But even conservative shaping assumptions imply hundreds of cubic meters of granite reduced to dust through abrasion, and abrasion is slow. Before we assign hours to that volume, before we convert cubic meters into man-days and man-years, one more variable must be examined with equal precision. The granite does not shape itself. It is the interface between tool and stone, copper against quartz, sand between them, that determines the tempo of construction. To understand that interface, we must examine the tools that touch the stone. Subscribe to our channel if you love this journey. To understand the granite, we must understand what touched it. Old Kingdom Egypt did not possess iron tools. It did not possess hardened steel. The metal technology available during the reign, traditionally attributed to Khufu, was based primarily on copper, often alloyed with small amounts of arsenic. True tin bronze appears later in Egyptian history, though limited early forms may have existed in trace quantities. For the 4th dynasty, arsenical copper remains the most defensible assumption. Pure copper is a soft, ductile metal. On the Mohs scale, it ranks near 3. Its yield strength, the stress at which it permanently deforms, is modest, typically in the range of 50 to 100 megapascals depending on processing. Arsenical copper improves hardness and strength slightly. The addition of even 1 to 3% arsenic can increase strength and wear resistance. Yield strength may rise toward 150 megapascals under favorable conditions, but even at its best, arsenical copper remains dramatically softer than quartz embedded within granite. Granite's quartz crystals measure 7 on the Mohs scale. When copper slides across them, it does not carve into the quartz. The quartz abrades the copper. This mechanical asymmetry is central. If copper were used alone against granite, it would smear and deform before removing significant material. Therefore, direct cutting by metal edge is not the operative mechanism. The metal tool serves another function. Archaeological evidence from reliefs, tool marks, and surviving implements suggests several key instruments: flat copper saws, tubular copper drills, chisels, and dolerite pounding stones. The saws are often depicted as long blades, possibly tensioned, used in reciprocating motion. Tubular drills appear as hollow cylinders rotated vertically, producing circular cores. But the copper in these tools was not expected to bite into granite like modern carbide teeth. Instead, it carried abrasive sand. Quartz sand, abundant along the Nile and in desert environments, possesses the same hardness as quartz within granite. When trapped between copper and stone, sand grains become the actual cutting agents. As the copper blade moves back and forth, sand grains are dragged across the granite surface under pressure. Each grain acts as a micro-cutting point, fracturing tiny fragments from the stone. The copper blade itself functions primarily as a pressure distributor and motion transmitter. In this abrasive cutting model, the metal does not need to be harder than the stone. It must only be sufficiently rigid to press the abrasive into the surface while maintaining consistent motion. However, there is a consequence. The same quartz grains abrade the copper tool. Edge retention under quartz abrasion becomes limited. As copper slides against sand and granite, its surface deforms plastically. Edges round off. Saw teeth, if present, would not remain sharp for long. Tubular drill rims would wear down, requiring reshaping. The metal is consumed gradually, not explosively but continuously. Work hardening plays a role. Copper, when hammered or cold worked, increases in hardness through dislocation accumulation in its crystal lattice. Egyptian smiths were aware of this phenomenon empirically. Repeated hammering followed by annealing cycles allowed them to shape tools and restore some hardness. But work-hardened copper remains far below the hardness of quartz. It delays deformation. It does not eliminate it. Consider yield strength comparison more precisely. Granite's compressive strength may exceed 200 megapascals. Copper's yield strength under Old Kingdom metallurgy likely remained below that figure. Under localized stress at contact points with quartz grains, copper yields. This yielding is not catastrophic failure, but gradual deformation. The tool face flattens, the geometry changes, cutting efficiency declines. Thus, the tool must be periodically removed, hammered back into shape, possibly annealed in a charcoal furnace to relieve internal stresses, then returned to service. Each cycle consumes time. Each reheating consumes fuel. Each remelting, if required, consumes metal mass and energy. Smelting copper in the Old Kingdom required mining ore, crushing it, roasting to remove sulfur, and reducing it in a charcoal-fueled furnace. Charcoal production demands wood. Wood demands land or trade. Every kilogram of copper placed into a saw blade carries upstream energy costs invisible in the finished monument. Now examine the mechanics of abrasive sawing more closely. Imagine a flat copper blade resting on a granite block. Sand and water form a slurry between blade and stone. Two workers pull the blade back and forth. Downward pressure must be applied to embed sand grains into the contact surface. As motion continues, sand grains roll, slide, and fracture. Some grains crush, some embed into the copper, some embed into the granite surface temporarily. Material removal occurs as microfractures propagate under localized stress. Removal rate depends on several variables: applied pressure, stroke length, stroke frequency, sand grain size, slurry concentration, and tool rigidity. Increase pressure excessively and the copper deforms more rapidly, reducing effective abrasion. Decrease pressure and removal slows. There exists an optimal operating window, but it is narrow. Tubular drilling follows similar principles. A hollow copper cylinder is rotated manually while abrasive slurry occupies the annular gap between drill rim and stone. The rim presses sand grains against the granite surface, grinding downward gradually. The result is a cylindrical cavity and a central core. Spiral striations, sometimes observed in surviving cores, suggest rotational motion under abrasive conditions. Yet again, the copper rim wears. Its thickness diminishes. It must be reworked or replaced. Edge retention, therefore, becomes a logistical parameter. How many linear meters of sawing can a copper blade perform before deformation reduces efficiency by half? How many drill penetrations can a tubular tool complete before its rim requires reshaping? Experimental archaeology suggests that wear is measurable and significant. Dolerite pounding stones introduce another dynamic. Dolerite, harder than granite, can chip away at surfaces through repeated impact. Quarry faces at Aswan display pitted surfaces consistent with pounding. However, pounding is effective for rough detachment, not fine surface finishing. It produces irregular fracture surfaces requiring subsequent smoothing by abrasion. Thus, granite shaping likely involved a two-stage process: impact for bulk removal, abrasion for precision. Now consider scale. If hundreds of granite blocks required flattening and squaring, each face requiring hours of abrasive motion, the cumulative tool wear becomes substantial. Copper mass consumed is not trivial. Even if individual losses are measured in grams per hour, thousands of hours accumulate into kilograms. Multiply by number of concurrent tools, and copper demand grows. Resharpening cycles imply downtime. A blade removed from service for hammering or annealing is not cutting stone. The workforce must either possess surplus tools to rotate in or accept reduced productivity during maintenance. Both options require planning and resources. Charcoal consumption for annealing and smelting must also be considered. Ancient furnaces were inefficient by modern standards. Maintaining high temperatures to melt copper demands sustained airflow and fuel input. Charcoal production itself is labor-intensive. The copper supply chain stretches from Sinai mines to Nile transport to Giza workshops. In this light, copper tools are not incidental accessories. They are consumable industrial inputs in a large-scale project. The abrasive sand itself, while abundant, must be managed. Grain size influences cutting rate. Too coarse, and scratches deepen without uniform smoothing. Too fine, and removal slows dramatically. Sand must be replenished frequently as grains fracture into smaller particles. Water must be supplied to form slurry. In arid environments, water is not trivial. All these factors converge on one variable: rate. If copper serves merely as a pressure carrier for quartz sand, and if quartz abrades both granite and copper simultaneously, then removal is inherently gradual. The question is not whether granite can be cut this way. It demonstrably can. The question is quantitative. Under realistic Old Kingdom conditions, human-powered motion, hand-forged copper tools, charcoal-fired annealing, what was the average cubic centimeter removal rate per worker per hour? Because once that number is established, even approximately, it can be multiplied by 3,000 cubic meters and compared against 2 decades of labor. Possibility is not the issue, throughput is. Even if cutting granite with copper and sand is physically achievable, the decisive variable remains unresolved. How fast? In the modern era, speculation about ancient stoneworking has given way, at least in part, to replication. Rather than assume what copper tools could accomplish, researchers have attempted to reproduce Old Kingdom techniques using reconstructed implements, comparable materials, and controlled measurement. Among the most cited of these efforts are the experiments conducted by Dennis Stocks, who systematically tested copper saws, tubular drills, and dolerite pounders against granite blocks under conditions designed to approximate ancient practice. The results were neither sensational nor dismissive. They were incremental. Granite could indeed be cut, but it yielded reluctantly. In sawing experiments using a flat copper blade with quartz sand slurry, material removal rates were measured in millimeters per hour, not centimeters. Under steady 2-person operation, a groove might deepen by approximately 1 to 3 millimeters per hour, depending on pressure and sand replenishment. In volumetric terms, this translated into a removal rate on the order of a few cubic centimeters per minute at best, and often less when tool wear or fatigue intervened. To visualize that pace, imagine cutting a slot 5 millimeters wide across a granite surface. At 2 millimeters of depth per hour, the groove would require 5 hours to reach 10 millimeters deep. For a block face requiring flattening over a square meter, the cumulative surface abrasion becomes substantial. The tool moves continuously, but the stone retreats slowly. Tubular drilling produced similar results. Using a hollow copper cylinder rotated manually with abrasive slurry, penetration rates were measured at roughly 1 to 2 millimeters per hour under sustained effort. Drill cores extracted during these experiments displayed striations consistent with abrasive grinding rather than cutting by a hardened edge. The copper rim wore down progressively, requiring reshaping after limited advance. Each few centimeters of penetration represented multiple hours of concentrated labor. Dolerite pounding, used primarily for rough quarrying, achieved faster bulk removal. Repeated impact could chip away granite surfaces more aggressively than abrasion alone. Yet pounding produces uneven topography. It fractures along grain boundaries unpredictably. To achieve flat mating surfaces suitable for chamber construction, abrasion must follow impact. Copper wear was measurable and persistent. After hours of sawing, blade edges rounded. Surface faces became concave or distorted. In some trials, measurable copper mass was lost in the form of fine particles or adhered to the granite surface. Tools required periodic hammering to restore shape. In some cases, partial remelting was necessary after extended use. These experimental observations can be translated into measurable metrics. Suppose a sawing operation removes approximately 3 cubic centimeters per minute under optimal conditions. Over an hour, that equates to 180 cubic centimeters. Over an 8-hour workday, roughly 1,440 cubic centimeters, about 1.4 liters of granite, removed per tool pair per day. Even if we adopt an optimistic rate of 5 cubic centimeters per minute, daily removal per tool might approach 2.4 liters. Now consider cubic meters. 1 cubic meter equals 1 million cubic centimeters. At 1,440 cubic centimeters per day, it would take approximately 694 workdays for a single tool team to remove 1 cubic meter of granite purely through abrasion. Even at the optimistic 2,400 cubic centimeters per day, the figure remains around 417 days. Of course, blocks are not carved from solid cubes entirely by abrasion. Rough shaping by pounding reduces the volume requiring fine removal, but flattening faces, squaring edges, and achieving dimensional accuracy still demand significant abrasive time. Tubular drilling metrics reveal similar constraints. If penetration proceeds at 1.5 millimeters per hour, drilling a 10-centimeter deep hole requires roughly 67 hours of continuous rotation. Multiply that by the number of required holes for architectural features or decorative coring, and the labor accumulates. Tool replacement frequency becomes a logistical parameter. If a copper saw loses effective geometry after, say, 10 to 20 hours of abrasive contact and requires reshaping taking perhaps an hour of skilled hammering and annealing, then productive time decreases by measurable fractions. A rotation system with spare tools could mitigate downtime, but this implies greater copper inventory and greater smelting capacity. Energy expenditure per worker also matters. Sustained sawing or drilling demands continuous mechanical input. Human metabolic output during heavy labor averages roughly 300 to 400 watts sustained over several hours. If 2 workers operate a saw, combined power input may approach 600 to 800 watts. Over an 8-hour day, that equates to roughly 17 to 23 megajoules of metabolic energy expended per pair, though only a fraction of that converts into effective fracture work. Much dissipates as heat and inefficiency. Comparing this metabolic energy to estimated fracture energy requirements per cubic meter suggests that the timescales observed experimentally are not anomalous. They reflect physical limits of human-powered abrasion against a hard, crystalline rock. Variability must be acknowledged. Experimental conditions are modern approximations. Skilled ancient workers, operating daily from youth, may have optimized technique beyond what brief modern trials achieve. Conversely, laboratory settings often allow controlled conditions, fresh tools, and consistent sand supply not always guaranteed in ancient field environments. Thus, we can define optimistic and conservative scenarios. In an optimistic case, assume 5 cubic centimeters per minute removal during active abrasion, minimal downtime for tool maintenance, and coordinated team rotation, allowing near-continuous operation during work hours. In a conservative case, assume 2 cubic centimeters per minute, with 20% downtime for reshaping and sand replenishment. Under optimistic assumptions, one tool team might remove roughly 2.4 liters of granite per day. Under conservative assumptions, perhaps closer to 1 liter per day. Scale that across multiple teams, and daily throughput increases proportionally. If 50 teams worked simultaneously on granite finishing, optimistic daily removal could approach 120 liters, 0.12 cubic meters per day. Over 200 effective working days per year, that yields 24 cubic meters annually. Over 20 years, approximately 480 cubic meters. But the granite volume inside the Great Pyramid approaches 3,000 cubic meters. Even accounting for rough shaping reducing final removal needs, the discrepancy becomes visible. Increase the number of teams to 200, and optimistic annual removal rises to roughly 96 cubic meters, yielding 1,920 cubic meters over 20 years. Closer to target, yet still contingent on idealized efficiency and uninterrupted coordination. These are illustrative calculations, not final verdicts. They depend critically on assumed removal rates and number of concurrent teams dedicated exclusively to granite shaping. Limestone block production, ramp construction, hauling, and administrative tasks all competed for labor allocation. The experiments demonstrate possibility. Granite can be cut with copper and sand, dolerite can detach blocks, tubular drills can penetrate, but the measured speeds are slow in absolute terms. A single block requiring perhaps several weeks of concentrated labor is entirely plausible within a large workforce. Precision craftsmanship over months does not strain imagination. The tension emerges only when one block becomes 100, when 100 becomes 1,000, when cubic centimeters become cubic meters, when days become decades. Measured removal rates, translated into volumetric throughput, accumulate quietly at first, then suddenly, one block is manageable. But what happens when we multiply? Take a single granite block. Not the entire chamber, not the mythic weight of the monument, just one representative stone of the kind placed within the inner structure of the Great Pyramid at Great Pyramid of Giza. Let us choose a moderate example, not the largest 70-ton ceiling beam, but a structural wall block weighing roughly 25 tons. At a granite density of approximately 2,700 kilograms per cubic meter, such a block would occupy just over 9 cubic meters of volume. 9 cubic meters. That is the raw mass extracted from the quarry at Aswan. But the quarry block does not emerge in perfect geometric form. It is detached by pounding, leaving uneven surfaces. It must be squared. Its faces must be flattened. Its edges must be aligned so that it integrates into a chamber wall with controlled joints. The first distinction is critical: rough shaping versus precision finishing. Rough shaping at the quarry could remove perhaps 70 to 80% of irregularities through dolerite pounding. This is impact work, heavy, repetitive, capable of breaking protrusions and approximating rectangular form. But pounding alone cannot produce flat surfaces suitable for tight mating joints. It leaves ridges and depressions that require abrasion. Let us assume that after rough shaping, the block still requires removal of an average of 2 centimeters across each face to achieve acceptable flatness and dimensional control. For a block roughly 2.5 meters by 1.5 meters by 1.2 meters, proportions consistent with interior granite elements, the total surface area approaches approximately 15 square meters. Removing 2 centimeters uniformly across 15 square meters equates to 0.3 cubic meters of material. That is 300 liters of granite reduced to powder. At experimental abrasive removal rates discussed previously, optimistically 2.4 liters per tool team per day, conservatively closer to 1 liter, the finishing phase alone becomes substantial. Under optimistic conditions, removing 300 liters would require roughly 125 days of continuous abrasive work by a single team. Under conservative conditions, 300 days, but that assumes one team per block. In practice, multiple teams might work simultaneously on different faces. Suppose 4 teams operate concurrently, each on a separate surface. Optimistically, the finishing phase might compress to roughly 30 to 40 days, conservatively perhaps 75 days. Now include rough shaping. Dolerite pounding is faster than abrasion but still laborious. Experimental replication suggests that detaching and roughly squaring a large granite block may require several weeks of concentrated impact labor by multiple workers. Let us assign conservatively 20 days of pounding and initial shaping before abrasion begins. Thus, a moderate 25-ton block may require between 50 and 100 total labor days of concentrated stoneworking effort, depending on efficiency assumptions and team allocation. Now consider drilling. Portcullis blocks and certain architectural elements required slots, channels, or precise openings. If a block required, for example, 4 drilled recesses, each 10 centimeters deep, and penetration rate is approximately 1.5 millimeters per hour, each hole would require around 67 hours of drilling. 4 holes total roughly 268 hours. With 2 workers rotating shifts, that equates to approximately 17 worker days. Add this to finishing time. Under optimistic assumptions, our representative block might demand approximately 70 to 90 worker days of direct stone shaping and drilling labor. Under conservative assumptions, perhaps 120 to 150 worker days. Let us take a middle figure, 100 worker days per block. Now scale. The granite mass within the pyramid approaches 8,000 tons, roughly 3,000 cubic meters. If average block size were 9 cubic meters, that would imply approximately 330 large blocks. But this simplification is deceptive. The granite inside the pyramid includes both massive beams and smaller portcullis slabs. Some beams weigh 60 to 70 tons, representing over 20 cubic meters each. Others are smaller. If we approximate an average block size of 10 cubic meters, then 3,000 cubic meters corresponds to roughly 300 blocks. If average size is smaller, say 5 cubic meters, block count doubles to 600. Let us adopt 400 blocks as a working midpoint for scaling purposes. At 100 worker days per block, 400 blocks require 40,000 worker days. Divide that by 300 effective working days per year, allowing for seasonal constraints, and we obtain roughly 133 worker years. That number seems modest, but it represents only finishing and shaping labor for granite, assuming our optimistic to moderate estimates are accurate and that multiple teams work in parallel. Now consider labor allocation. If 20 teams of skilled stoneworkers were assigned full-time to granite finishing, and each team represents 2 workers, that is 40 workers. At 40 worker days expended per calendar day, annual capacity becomes 12,000 worker days. Under that arrangement, 40,000 worker days would require just over 3 years. But this assumes continuous focus exclusively on granite shaping, uninterrupted by tool maintenance, transport delays, or competing construction demands. It also assumes the finishing requirement per block is limited to 2 centimeters uniformly, a figure that may be optimistic if quarry detachment left greater irregularities. Now widen the calculation. Suppose finishing removal averaged not 0.3 cubic meters per block, but 0.5 cubic meters due to irregular quarry surfaces. That increases removal by 66%. Abrasive timescales proportionally. If per block labor rises to 150 worker days, then 400 blocks require 60,000 worker days. With 40 dedicated workers, that stretches beyond 5 years. Increase block count to 500, and labor approaches 75,000 worker days. With 40 workers over 6 years. And remember, this accounts only for shaping and drilling, not extraction at Aswan, not river transport, not hauling up the plateau, not ramp construction, not limestone block production, not chamber alignment, not casing stone finishing. Now convert granite labor into a percentage of total project capacity. If the broader workforce numbered 20,000 during peak flood seasons, but only a fraction were skilled stoneworkers, perhaps a few hundred, granite shaping likely relied on a small specialized group. Granite was not the bulk material, limestone dominated, but granite was structurally critical and required precision.
Assume 200 skilled workers assigned to granite at various stages: quarrying, transport preparation, finishing. At 200 worker days per calendar day, annual output becomes 60,000 worker days. Under this scenario, 60,000 worker days of granite shaping could be completed in roughly 1 year.
But such concentration may be unrealistic given simultaneous demands across the construction site. Skilled labor was finite, copper tools were finite, transport windows were seasonal. Thus, granite shaping may not have been a full-scale industrial operation running at maximum parallelization from day one. It likely progressed in phases aligned with chamber construction schedules, and this is where scaling becomes revealing. One block requiring 2 or 3 months of concentrated effort is entirely plausible within an organized state. 10 blocks, even 50, remain plausible.
But hundreds accumulate into years of specialized labor.
Whether that accumulation comfortably fits within the range traditionally assigned to Khufu depends not on possibility, but on allocation. 40,000 worker days may seem small against millions of total project labor days. Yet those 40,000 must be concentrated within a narrow craft domain, supported by copper production, sand supply, charcoal fuel, and coordination with structural sequencing. The arithmetic does not declare impossibility. It introduces compression, and compression leads to a final, unavoidable comparison. Place the granite labor requirement beside a rain measured in 2 decades, and ask whether the numbers align cleanly or only under the most efficient assumptions imaginable. The clock begins not with stone, but with a name. The Great Pyramid on the Giza Plateau is conventionally attributed to the 4th dynasty pharaoh Khufu, known to the Greeks as Cheops. His reign is generally dated to approximately 2589 to 2566 BCE, though exact chronology varies slightly depending on king lists and astronomical retrocalculations. Most reconstructions place his rule somewhere between 23 and 27 years. That span defines the traditional construction window. The attribution rests primarily on archaeological evidence discovered within the pyramid itself. In the upper relieving chambers above the king's chamber, quarry marks painted in red ochre include work gang inscriptions bearing the royal name Khufu. These are not monumental hieroglyphic proclamations carved for public view. They are internal markings, likely left by construction crews, referencing teams with names such as the Friends of Khufu. Their presence strongly links the building phase to his reign. There are no detailed administrative records describing daily progress, no surviving project logs recording how many blocks were placed each year. The Old Kingdom did not leave behind engineering manuals. Much of what is known about the pyramid's construction derives from archaeology, material culture, and inference. Some scholars have raised questions over the centuries. A minority have suggested that construction may have begun late in the reign of Khufu's predecessor, or continued briefly under his successor, Djedefre. Others have scrutinized the authenticity of the quarry marks, though mainstream Egyptology considers them credible and consistent with other Old Kingdom inscriptions. The overwhelming scholarly consensus maintains that the Great Pyramid was constructed primarily during Khufu's reign. Even if minor chronological flexibility is allowed, a preparatory year before formal accession or finishing touches after death, the working window remains finite. It does not expand to a century. It does not stretch across multiple dynasties. At most, it shifts by a handful of years. For engineering analysis, therefore, a 20 to 27-year time frame is reasonable. To avoid exaggeration, let us adopt 25 years as a central estimate. Now the arithmetic tightens. In previous scaling, we approximated granite shaping and finishing labor on the order of 40,000 to 60,000 worker days under moderate assumptions. That figure depends heavily on removal depth, tool efficiency, and block count. Let us carry forward a conservative midpoint of 50,000 worker days devoted specifically to granite extraction, finishing, and drilling. Convert worker days into worker hours. Assuming an 8-hour effective labor day, realistic given the physical intensity of abrasive stonework, 50,000 worker days equal 400,000 worker hours. Divide 400,000 worker hours by 25 years. The annual requirement becomes 16,000 worker hours per year. Now account for seasonal constraints. The Nile flood season, when agricultural laborers were most available, lasted roughly 3 to 4 months. However, skilled stoneworkers likely worked year-round, supported by state provisioning. To avoid artificially compressing time, let us assume 250 effective working days per year for granite crews. 16,000 worker hours per year divided by 250 days yields 64 worker hours required per working day. That corresponds to 8 workers operating continuously for 8 hours per day on granite shaping. At first glance, this appears entirely manageable. But this is the moderate scenario. If finishing requirements were underestimated, if per block removal was closer to 0.5 cubic meters rather than 0.3, total granite shaping might approach 75,000 worker days. That equals 600,000 worker hours. Spread across 25 years, that becomes 24,000 worker hours annually. Divided across 250 days, 96 worker hours per day. 12 workers working full shifts. Still plausible, now increase block count. If total granite volume slightly exceeds 3,000 cubic meters due to measurement uncertainties, or if wastage during shaping was greater than assumed, total labor may approach 100,000 worker days. That equals 800,000 worker hours. Spread over 25 years, 32,000 hours annually. Divided across 250 days, 128 worker hours per day, 16 full-time workers. Even at this elevated estimate, granite shaping does not appear to demand thousands of craftsmen simultaneously. The numbers do not explode uncontrollably. They compress, but they remain within the scale of a specialized labor corps. However, these calculations represent only finishing and drilling. They exclude quarry extraction time at Aswan. If detaching and rough shaping each large block required additional weeks of labor before transport, those hours must be added. Suppose quarry detachment averaged 30 worker days per block across 400 blocks. That equals 12,000 additional worker days, or 96,000 worker hours. Spread across 25 years, that adds roughly 3,840 hours per year, another 15 worker hours per day. Now granite labor begins to approach 150 worker hours per day under moderately conservative assumptions. That equals roughly 19 workers operating continuously. Again, not implausible. But this presumes uninterrupted allocation of skilled crews dedicated solely to granite tasks for 25 consecutive years. In reality, granite work would have been phased. The King's Chamber and relieving chambers were built at specific stages of pyramid height. Granite beams could not be installed until lower courses were complete. Thus, granite shaping likely intensified during certain years rather than spreading evenly across the entire reign. If granite shaping was concentrated into, say, 15 effective years rather than 25, annual labor requirements increase by 2/3. Under the 800,000-hour scenario compressed into 15 years, annual demand becomes roughly 53,000 hours. Divided by 250 days, 212 worker hours per day, 26 full-time workers. Now the margin narrows. Add tool maintenance time, add smelting labor for copper replacement, add transport handling crews at Aswan and Giza. Each component draws from the same finite labor pool. The broader pyramid project required quarrying and placing approximately 2.3 million limestone blocks. Ramp construction, casing stone finishing, worker provisioning, and administrative oversight all competed for manpower. The granite component may represent only a fraction of total mass, but it required specialized tools and higher precision. Its labor cannot simply be merged with unskilled hauling crews. The 20 to 27-year clock therefore acts as a constraint, not a suggestion. Within it must fit limestone extraction, ramp building, alignment, casing placement, and granite shaping, all without evidence of prolonged political disruption. Does the granite workload alone break the timeline? Under optimistic assumptions, no. Under moderate assumptions, it compresses but fits. Under conservative assumptions, particularly if work was phased rather than evenly distributed, the schedule tightens noticeably. The arithmetic does not yet declare contradiction, but it does reveal dependence on sustained efficiency. And granite, formidable as it is, represents only one logistical layer in a far larger machine. Because cutting stone is not the only variable that consumes time, energy, and coordination. 800 kilometers south of Giza, the granite begins its journey in the quarries of Aswan. The stone there is not hypothetical. The quarry faces remain, scarred and pitted, bearing silent testimony to the violence required to free granite from bedrock. Extraction did not begin with saws, it began with impact. Dolerite, a hard, igneous rock tougher than granite, was fashioned into pounding stones, rounded hammering tools weighing several kilograms. Quarry workers struck the granite repeatedly, carving channels along intended block boundaries. The unfinished obelisk at Aswan, still partially attached to bedrock, provides a vivid cross-section of this method. Trenches were cut around the perimeter by relentless impact, gradually isolating a massive stone form from the surrounding matrix. The quarry face evidence is clear. Shallow hemispherical indentations cover extraction surfaces, each mark the result of a blow. Over thousands of strikes, grooves deepened. The process was not elegant. It was attritional. Granite fractures along microstructural weaknesses, but not predictably. Workers had to monitor cracks carefully to avoid catastrophic splits that would ruin a block. To detach a 50-ton granite beam, approximately 18 to 20 cubic meters in volume, trenches perhaps 50 centimeters wide might need to be pounded along 3 sides before undercutting. The depth of such trenches could reach 1 to 2 meters, depending on bedrock configuration. Experimental replication suggests that a single worker wielding a dolerite pounder might remove on the order of several kilograms of granite per hour during aggressive impact, though rates vary widely based on fatigue and fracture propagation. For large-scale trenching, teams would work in rotation. If we conservatively estimate that isolating and undercutting a 50-ton block required removal of roughly 10 cubic meters of surrounding granite as waste, a plausible figure given trench volume, and if bulk pounding removal proceeds at perhaps 0.02 cubic meters per worker hour under sustained conditions, then 10 cubic meters would require 500 worker hours. Spread across a team of 10 workers striking in coordinated shifts, that becomes 50 hours of active pounding, roughly 1 week of concentrated effort. In reality, inefficiencies, tool repositioning, crack monitoring, and fatigue likely doubled that time. 2 to 3 weeks per large block becomes a reasonable working estimate for detachment and rough isolation. Labor density at the quarry matters. The Aswan site spans a broad area with multiple extraction zones. It is plausible that several blocks were worked simultaneously. If 50 workers were dedicated to granite extraction during peak periods, perhaps 5 large blocks could be in active trenching at once. After detachment, blocks required rough shaping to reduce mass and eliminate protrusions. Pounding smoothed surfaces sufficiently for transport, but did not produce finished geometry. That rough shaping likely added additional days of labor per block. Now the stone must move. The Nile was the primary artery of transport. Granite blocks were hauled from quarry to riverbank, loaded onto barges, floated downstream during the inundation season when water levels were high, and offloaded near Giza. Loading a 50-ton block onto a wooden barge demands careful staging. Sledges, rollers, and earthen ramps likely facilitated movement. Archaeological depictions from later periods show large stone transport on sledges pulled by teams of workers over lubricated surfaces. Friction coefficients for sled-on-wet sand systems can be reduced to manageable levels, but pulling 50 tons still requires coordinated force. If a sledge bearing 50 tons encounters a friction coefficient of 0.2, the required horizontal force equals roughly 10 tons force, approximately 100 kilonewtons. A single worker can sustain perhaps 300 newtons of pulling force for extended periods. Thus, roughly 300 to 350 workers might be required to pull such a load on level ground under ideal lubrication. On ramps or inclines, the number increases. However, transport from quarry to river likely involved shorter distances and gradual slopes. Teams could rotate. The labor is heavy but not impossible within an organized state. The Nile flood window constrained scheduling. Barges capable of carrying 50 to 70-ton loads required sufficient draft. High inundation months provided ideal depth and current assistance for downstream travel. Outside flood season, transport capacity diminished. The distance from Aswan to Giza is roughly 800 kilometers by river. Downstream travel with current assistance may have taken several weeks, depending on conditions and stops. Let us estimate a conservative transit time of 20 to 30 days, including loading and unloading. Thus, a single block's transport cycle, from detachment to arrival at Giza, might span approximately 2 months when accounting for quarry work, staging, river transit, and offloading delays. Now consider throughput. If one barge can carry one 50-ton block, and if round-trip logistics, including return upstream travel, require perhaps 60 to 90 days, then each vessel might complete 4 to 6 delivery cycles per year under ideal conditions. However, upstream return against current is slower and more labor-intensive. Realistically, perhaps 3 to 4 cycles annually per vessel. If 10 barges were dedicated to granite transport during peak flood seasons, annual delivery capacity for large blocks might reach 30 to 40 units. Over 20 years, that equates to 600 to 800 large block deliveries, sufficient to account for granite requirements, even with conservative margins. Smaller blocks could be transported in multiples per vessel, increasing throughput. Offloading at Giza introduced another phase. Blocks were transferred from riverbank to sledges and hauled up to the plateau. The distance from harbour to construction site was likely several kilometres, depending on Nile Channel configuration in the Old Kingdom. Again, labour-intensive but scalable with workforce size. Maximum annual throughput therefore appears feasible. Even if only 20 large granite blocks reached Giza per year, over 20 years that yields 400 blocks, consistent with earlier scaling estimates. Transport does not appear to be the limiting factor if state resources were mobilized efficiently. The Nile provided a natural conveyor belt, and Egyptian administrative capacity in the Old Kingdom was sophisticated enough to coordinate large labor projects. Yet transport assumes steady extraction at Aswan. Extraction assumes sufficient dolerite tools and organized labor. Transport assumes functional barges and seasonal predictability. Granite logistics form a chain. Each link must operate without prolonged interruption to maintain annual averages. If extraction and river transport can deliver the necessary volume within 2 decades, then the physical movement of stone may not be the bottleneck. But transport is only meaningful if shaped granite can be produced at pace once it arrives. And shaping at Giza depends on something less visible than barges or sledges. It depends on copper. Even if the stone can be quarried and floated north in sufficient quantity, the tools required to finish it must exist in equal measure, continuously, predictably, and in large numbers. Because stone does not wait for metal, granite is stubborn but copper is fragile. The interface between the two defines the tempo of the entire operation. Abrasive cutting works because copper carries quartz sand, but every moment of contact erodes the tool. Copper wears, it deforms, it must be reshaped, annealed, and sometimes entirely recast. The implications ripple across the project, reaching deep into energy, material, and labor logistics. To quantify tool wear, we must begin with measured removal rates. Experimental archaeology suggests that a pair of workers using a flat copper saw with abrasive slurry can remove roughly 2 to 5 cubic centimeters of granite per minute under sustained conditions. Each hour, a single saw may see 120 to 300 cubic centimeters of stone removed. The corresponding copper mass loss, though small in absolute terms, accumulates quickly. Replicated tests indicate that for each hour of active abrasive cutting, a copper saw can lose several grams of metal due to plastic deformation and abrasion by quartz grains. Over days and weeks, this translates into kilograms of copper consumed per tool. Edge maintenance is continuous. After several hours of cutting, edges round, efficiency declines, and the tool must be removed for reshaping. Resharpening involves hammering, work hardening, and annealing in a charcoal-fired furnace. Each cycle consumes additional time, labor, and fuel. When a blade is too worn to restore, it must be entirely melted down and recast into a new implement. Melting copper in the Old Kingdom was no trivial matter. Ore sourced from the Sinai Peninsula, both native copper and malachite-bearing rock, required mining, crushing, and roasting to remove sulfur or other impurities. The reduction process took place in small clay furnaces, fueled by charcoal. Even a single saw or drill might consume hundreds of grams of copper over its operational lifetime. Multiply that by the hundreds of blocks to be shaped, by the dozens of tools required for simultaneous work, and the mass of copper needed scales to metric tons. Consider an illustrative scenario. Suppose shaping all granite within the Great Pyramid required 400 tools operating over 2 decades, each losing 2 kilograms of copper cumulatively through wear, reshaping, or recasting. That alone implies 800 kilograms of copper, nearly a metric ton. Under more conservative assumptions, factoring higher wear, additional drilling tools, and spares to maintain continuous workflow, total copper requirements could easily approach 2 to 3 metric tons. Copper alone is insufficient. Its supply depends on ore yield, smelting efficiency, and fuel availability. Sinai mines yielded copper ore intermittently and with variable richness. Smelting efficiency in the Old Kingdom, particularly in small furnaces, is modest, perhaps 30 to 50%. To produce 1 kilogram of usable metal, 2 to 3 kilograms of ore might be required. Thus, producing 3 tons of usable copper demands roughly 6 to 9 tons of ore, excluding losses during transportation and handling. The smelting process also requires energy in the form of charcoal to achieve sustained temperatures above 1,100 degrees Celsius. Charcoal production consumes wood. Each ton of copper may require several tons of charcoal, depending on furnace efficiency. Charcoal itself represents a large fraction of energy cost, dense, portable, and capable of maintaining temperatures for multiple hours of melting. The cumulative wood demand for 2 to 3 tons of copper is therefore significant. Large-scale smelting would require substantial fuel logistics, wood sourcing, drying, transport, and storage, all coordinated alongside stone extraction and finishing. Energy is the hidden currency here. Every gram of copper lost represents work already performed, fuel expended, and labor applied. Every recasting cycle compounds the energy cost. Annealing cycles, hammering, reshaping. Each consumes time, oxygen-rich fire, and charcoal. The Old Kingdom bureaucracy would have had to supply not only copper and fuel, but skilled smiths capable of controlling temperature and preserving alloy quality. Even with modest tool loss per hour, scaled across decades of granite work, the mass of copper consumed, the frequency of recasting, and the fuel requirements become a logistical machine unto themselves. The copper cycle is continuous: extraction, smelting, transport, forging, deployment, wear, reshaping, recasting. Interruptions anywhere along this chain would throttle granite shaping. Without metal, the stone cannot yield. Wood consumption is particularly revealing. Charcoal is dense, but creating it consumes roughly 2 to 3 times its weight in wood. To supply 2 to 3 metric tons of copper, smelting may require 6 to 9 tons of charcoal, which in turn implies 12 to 27 tons of raw wood. That is forest-scale energy allocated solely to sustaining a tool chain for granite work. Consider energy in human terms. A single worker produces roughly 300 watts of sustained power over an 8-hour day, 2.4 megajoules per day. The mechanical energy delivered to cutting granite is only a fraction. Much dissipates in heat, friction, and deformation of copper. Charcoal provides thermal energy orders of magnitude greater. It is invisible but indispensable. Every gram of quartz removed depends upon fire elsewhere, transforming mineral and metal to maintain cutting tempo. Smelting yield, ore transport, fuel logistics, and tool maintenance form a feedback loop. One bottleneck propagates. If copper smelting falls behind, shaping slows. If fuel is insufficient, annealing cycles lengthen, tool deformation accumulates, and labor productivity declines. Granite cutting is therefore not merely mechanical, it is industrial in scope, constrained by invisible energy flows as much as by human hands. In this context, the sheer scale of coordinated metallurgy emerges as part of the puzzle. Tens of workers devoted to granite shaping require dozens of skilled smiths producing and maintaining copper implements supplied by a network of miners, transporters, and fuel gatherers. Energy cost underpins every stage, yet it is rarely visible in the archaeological record. Charcoal remnants, slag, and furnace remains hint at scale, but the full arithmetic of energy rarely penetrates popular narratives. Thus, the cutting speed problem encompasses more than physical removal rates. It includes tool wear, resharpening cycles, recasting frequency, smelting yields, fuel consumption, and wood procurement. Each factor multiplies across the decades-long schedule, converging upon a narrow bandwidth in which stone, tool, and energy must synchronize. Granite will not yield without copper. Copper will not function without fuel. Fuel will not arrive without labor, and labor will not operate without provisioning. The chain is visible only when measured cumulatively, in kilograms of stone removed, in grams of copper consumed, in tons of charcoal burned. Energy, invisible as air, governs the rhythm of the project. It determines throughput. It sets limits on what can be accomplished within 25 years. It forces us to account not only for human ingenuity, but for the material and thermodynamic reality that underpins every cut, every block, every chamber. And as energy constrains labor and tools, the question surfaces with renewed intensity. Even if manpower and tools exist, even if quarrying, transport, and cutting are synchronized, can the available energy sustain the pace required for granite to flow continuously from Aswan to Giza into precisely shaped blocks without interruption? Every stone moved, every copper saw swung, every granite block lifted is ultimately an energy transaction. To understand the Great Pyramid in terms of possibility, we must translate human effort, mechanical work, and transport into a single comparable unit, energy. Only then can the ceiling of feasibility emerge from abstraction. Human labor begins with metabolism. A single adult performing sustained heavy work generates roughly 300 watts of power over an 8-hour workday. In energy terms, that is approximately 2.4 megajoules per day, the metabolic output available for quarrying, pounding, sawing, and hauling. For larger crews, 50 to 100 skilled granite workers, plus transport teams, plus coppersmiths, daily energy input multiplies rapidly. 100 workers, each at 2.4 megajoules per day, collectively produce 240 megajoules of mechanical potential daily, though only a fraction translates into effective work. Fatigue, inefficiency, and environmental losses consume the remainder. Granite itself is not yielding. Its compressive strength, typically 130 to 250 megapascals, defines the minimum energy required to fracture and remove material. Experimental replication suggests that detaching a cubic meter of granite through pounding and abrasive methods demands on the order of 2 to 4 gigajoules, depending on desired precision. One small block requiring only partial finishing might still require hundreds of megajoules of labor energy, dwarfed only by the energy cost of lifting it. Lifting is a separate calculation. Many granite beams in the King's Chamber weigh 40 to 70 tons. Raising a 50-ton beam to a height of 43 meters involves gravitational potential energy, calculated as mass times gravity times height. 50 tons, 50,000 kilograms, lifted 43 meters against 9.81 meters per second, squared yields roughly 21 million joules, or 21 megajoules. This is per beam, per lift. Multiply by dozens of beams and the total reaches hundreds of megajoules. Even with mechanical advantage from ramps, sledges and inclined planes, energy expenditure cannot disappear. Friction and inefficiency absorb a substantial portion. Transport over land introduces further energy demand. Sledges gliding across sand face friction coefficients, typically estimated between 0.2 and 0.3. A 50-ton granite block on a sledge requires horizontal force in the range of 100 to 150 kilonewtons. Work, in joules, equals force times distance. A 1-kilometer haul at 100 kilonewtons requires 100 million joules, 100 megajoules, for a single block over that modest distance. Multiple trips, multiple blocks, and longer ramps multiply the requirement quickly. River transport is more energy efficient, taking advantage of buoyancy and current, but loading and unloading remain energy intensive, again dependent on manpower. Now consider the human scale. A single worker delivering 2.4 megajoules per day contributes only a tiny fraction of the mechanical energy needed for one block. To match the hundreds of megajoules required for lifting and transport, dozens of workers must coordinate simultaneously. And that does not account for quarrying, finishing, or copper tool maintenance. Cumulatively, across the 3,000 cubic meters of granite alone, energy demand approaches tens of terajoules when all processes, extraction, shaping, drilling, transport, lifting, are included. The limestone mass adds further millions of cubic meters, though its lower density and softer composition reduce per cubic meter energy cost. Here, food enters the equation. Human metabolism must be fueled. Each worker requires daily caloric intake to sustain energy output. A heavy laborer performing sustained work may require 4,000 to 5,000 kilocalories per day, roughly 16 to 21 megajoules of dietary energy. For 100 workers, daily consumption approaches 1.6 to 2.1 gigajoules, orders of magnitude above individual metabolic output due to inefficiencies in converting food into work. Annually, for sustained decades, total caloric demand becomes a critical factor in workforce planning. Agricultural surplus in Old Kingdom Egypt, derived from the inundation-fed Nile Valley, defines a ceiling. Fields produce staples sufficient to feed a population of hundreds of thousands, with surplus allocated to the state. Grain, vegetables, and protein sources supported laborers seasonally and year-round, but there were limits. Feeding 5,000 to 10,000 workers continuously, not counting administrative, artisan, or auxiliary crews, required careful provisioning and storage infrastructure. Shortages could delay work. Surpluses enabled the project to proceed at maximum efficiency. Fuel for copper smelting, charcoal for annealing, and wood for heating tools also draw from the same landscape. Each ton of copper produced requires several tons of charcoal, itself a derivative of wood resources. The energy embodied in charcoal is measured in gigajoules. Without adequate forest or trade supply, tool maintenance falters. Tool wear and labor capacity are thus inseparable from energy flow. Friction, mass, lifting, and abrasion are quantifiable. Human metabolic output is quantifiable. Food and fuel are quantifiable. When summed, these form an energy ledger for the Great Pyramid, a ledger that defines what is possible in a reign of 20 to 27 years. Every block moved is a transaction in this ledger. Every ounce of copper lost, every sledged ton of stone, every meal provided, every log burned contributes.
And here, in the stark arithmetic of energy, the subtle tension emerges. Even if labor and tools exist, even if transport is feasible, even if quarrying proceeds efficiently, the ceiling is not indefinite. Food and fuel impose a natural limit on how much stone can be shaped, moved and lifted at any given moment. Push beyond that limit and productivity falters. Delay the Nile flood, misallocate grain, miscalculate charcoal, and schedules slip.
In other words, energy, invisible and unglamorous, governs the tempo of construction as much as the genius of architects or the skill of masons. It is the hidden framework beneath the visible monument, and as we confront this ledger, we must ask, if food and fuel define the ceiling of possibility, are all other elements, labor, copper, transport, sufficient to keep the Great Pyramid within the allotted 20 to 27 years? Or do constraints accumulate, pressing against the king's lifetime, demanding that every calculation, every allocation, every ounce of energy be perfectly aligned? The pyramid was never built by a single hand, nor by a handful of masons. It was the product of a workforce organized on a scale that rivals the largest industrial enterprises of the ancient world. Estimating that workforce, however, is far from straightforward. Ancient records are sparse. Herodotus, writing centuries later, mentions hundreds of thousands of laborers, but his numbers are widely regarded as exaggeration. Modern archaeological analysis leans toward more moderate figures, perhaps 20,000 seasonal laborers, supplemented by 30,000 permanent staff, a combination of skilled craftsmen, haulers, engineers, and support personnel. These numbers represent a rotating system, with crews cycling through agricultural, administrative, and construction duties in response to seasonal rhythms, Nile inundations, and state demands. To model the impact of granite shaping within this broader workforce, we must consider three scenarios, each reflecting different assumptions about human efficiency, tool performance, and labor coordination. The first scenario assumes optimistic, high-efficiency removal. Here, abrasive copper saws operate at the upper bound of experimental rates, multiple teams work in parallel on the same block, and transportation and quarrying proceed without interruption. In this idealized model, one block might require roughly 50 to 70 worker-days of shaping and drilling. Scaling to 400 large blocks of granite, total labor approaches 25,000 worker-days over the entire construction window. Spread across a 25-year reign, that is roughly 1,000 worker-days per year. If seasonal rotation brings 20,000 laborers to the plateau during peak periods, granite shaping represents a fraction, perhaps 5%, of total workforce capacity. In this scenario, granite, though labor-intensive, does not monopolize the labor pool. It coexists with limestone quarrying, ramp building, casing placement, and administrative work. The second scenario is moderate efficiency. Tool wear, resharpening, and human fatigue reduce productivity. Abrasive removal rates are more conservative, and teams cannot be perfectly synchronized. Each block now demands 100 worker days. Across 400 blocks, that yields 40,000 worker days. Dividing over 25 years, the annual requirement is 1,600 worker days. Relative to a seasonal workforce of 20,000, this consumes approximately 8% of annual labor capacity. Granite remains manageable, but the buffer narrows. Minor delays, seasonal disruptions, or tool shortages begin to stress scheduling. The project can succeed, but only if coordination is maintained, supplies are timely, and no major bottlenecks emerge. The third scenario represents conservative assumptions. Tool efficiency is lower, abrasion slower, and finishing requirements higher due to irregular quarry surfaces. Each block demands 150 worker days. 400 blocks now require 60,000 worker days, roughly 2,400 worker days per year over 25 years. For a 20,000-strong seasonal workforce, Granite cutting consumes 12% of available labor, at first glance still within possible limits. But this does not account for competing tasks. Limestone extraction, ramp preparation, hauling, casing stone placement, copper smithing, and provisioning all draw on the same pool. When considered cumulatively, granite becomes a disproportionately labor-intensive fraction of the project, threatening to crowd other essential operations if not carefully scheduled. Rotational labor structures further complicate arithmetic. Seasonal farmers, conscripted during Nile inundation months, contributed their strength for 3 to 4 months, while permanent teams maintained continuity year-round. Granite shaping likely depended on the permanent skilled cohort, given the precision required and the expertise needed to manage abrasive copper tools. Thus, while the seasonal workforce augmented heavy hauling and general masonry, the permanent team carried the bulk of granite operations. Any lapse in tool supply, smelting, or transport within this skilled cadre would delay work disproportionately, illustrating that total worker numbers alone do not guarantee throughput. The distribution of skill and specialization matters. Under each scenario, it becomes evident that granite, though a minority of the pyramid's total stone volume, commands a strategic share of labor. Unlike limestone blocks, which were softer, more abundant, and more forgiving of less precise workmanship, granite demanded specialized skills, extended labor time per unit, and continuous tool maintenance. Its labor intensity is measured not merely in absolute hours but in opportunity cost. Every day a skilled worker spends shaping granite is a day not spent hauling casing stone, preparing ramps, or supervising alignment. The pyramid's construction is a system of interdependent processes. A bottleneck in one domain propagates through the entire operation. Energy, food, and material supplies also intersect with labor considerations. Skilled workers require adequate caloric intake to sustain the physical output necessary for abrasive shaping. Copper tools, charcoal for annealing, sledges, and transport infrastructure all compete for attention. Granite's demand is therefore multifaceted. It is physical, logistical, and administrative simultaneously. By scaling labor mathematically across scenarios, a picture emerges. Under optimistic assumptions, the pyramid could accommodate granite work comfortably within the seasonal and permanent labor pool. Under moderate assumptions, granite consumes a notable share of labor but remains feasible. Under conservative assumptions, granite begins to approach the limits of labor allocation, threatening to encroach on other critical operations and requiring careful scheduling, precise tool management, and uninterrupted energy supply. The calculations underscore a subtle tension. Granite is not the majority of the pyramid's mass, limestone dominates, yet its influence on construction timing, labor allocation, and tool management is disproportionately significant. Its difficulty, combined with the constraints of manpower, tool supply, and seasonal labor rotation, transforms a minority material into a potential project bottleneck. This is the essence of the cutting speed problem. A relatively small volume of the hardest stone dictates operational tempo, resource allocation, and ultimately, the feasibility of completing the pyramid within the finite window of a king's reign. And so, even as granite represents only a fraction of the total stone, it serves as the litmus test for the project's labor capacity, the hidden governor of the pyramid's schedule, and the measure against which the rest of the construction machinery must synchronize. The pyramid is more than granite. The majority of its mass consists of local limestone, quarried just a few kilometers from the plateau. Unlike granite, this stone is soft, relatively uniform and forgiving. Copper tools, dolerite pounding, and abrasion all perform far more efficiently on limestone than on the dense, quartz-rich granite transported from Aswan. Where granite demands meticulous finishing over weeks per block, limestone can be roughly shaped and placed in days. Experiments suggest that a skilled team can cut and position a cubic meter of limestone in a fraction of the time required for the same volume of granite, even under conservative assumptions. Limestone blocks numbered in the millions. Estimates range from 2.3 to 2.5 million units. Their sheer quantity dominates the pyramid's bulk, yet in aggregate, they do not necessarily dominate the schedule. Limestone cutting can scale horizontally. Multiple crews can operate simultaneously across a broad quarry front, each producing blocks for immediate placement. Transportation from nearby quarries involves short sledges and modest ramp inclines. Because the stone is easier to work, turnover is rapid, and throughput can keep pace with construction demands with a large but not extraordinary workforce. In essence, limestone construction scales efficiently, capable of filling daily quotas without inducing significant project bottlenecks. Granite, in contrast, is inherently rigid. Its scarcity within the pyramid, concentrated in critical internal features like the king's chamber, relieving chambers and portcullis blocks, does not diminish its influence on the construction schedule. Each granite block requires specialized extraction, precise shaping, drilling where necessary, and careful transport and installation. The labor investment per cubic meter is many times greater than that for limestone. In scheduling terms, granite is a high-intensity, low-volume component. Its slow cadence contrasts sharply with the rapid turnover possible for limestone blocks, making it the prime candidate for the project's critical path. In project management, the critical path defines the timeline. The slowest, most constraining process determines the minimum duration required for overall completion. No matter how efficiently limestone production proceeds, construction cannot advance beyond points constrained by granite availability. If the king's chamber cannot receive its beams, or the portcullis cannot be installed, other structural elements may stall or require temporary accommodation. Every day of delay in granite processing ripples outward, forcing coordination adjustments for limestone placement, ramp progression, and workforce allocation. Limestone throughput is flexible and expansive, but granite precision is rigid and bottlenecked. This disparity between materials creates a paradox of scale. While the majority of stones are comparatively easy to work, they cannot compensate for the slow-moving minority of granite blocks that define internal precision. Granite's labor demands, cutting duration, and transport logistics impose limits on the maximum feasible daily installation rate for the pyramid as a whole. The project does not merely sum labor across stone types. It is gated by the slowest process. High-volume limestone production cannot accelerate completion if granite shaping lags. Every cubic meter of granite is a potential constraint, a time-bound choke point that dictates the pace of assembly and the effective utilization of seasonal labor. When we analyze the numbers, the tension becomes clear. Granite shaping may require months of concentrated effort per block, while thousands of limestone blocks can be cut, transported, and installed in a single season. Yet the schedule for completing key internal chambers cannot outpace the slowest granite block. In this sense, granite is not the mass problem, but the precision problem, the lever that controls the overall timeline. The workforce, no matter how large, cannot simultaneously accelerate granite processing beyond physical and tool-imposed limits. The slow advance of high-precision stone governs the rhythm of the entire enterprise. Even if we allow for overlap, crews cutting limestone in one zone while granite finishing continues elsewhere, the pyramid remains bound by points where granite must arrive and fit precisely. Placement delays, misalignment, or insufficient supply of prepared granite blocks reverberate through the project, forcing rescheduling, idle time for other teams, and increased administrative coordination. It is the paradox of high volume versus high intensity work. Abundance cannot override constraint. Limestone is abundant but flexible. Granite is scarce but rigid. By framing the construction sequence this way, we see that the Great Pyramid's timeline is not merely a matter of total stone volume or workforce size. It is the interplay of material properties, tool limitations, energy availability, and labor allocation. Granite, with its stubborn hardness, low removal rate, and high precision requirements, asserts itself as the controlling factor. It is the bottleneck that defines the rhythm and pace of the project, even though it represents only a fraction of the total mass. If granite truly governs the critical path, the implications are profound. The arithmetic of workforce hours, cutting speed, transport cycles, and energy consumption must all align perfectly to sustain a continuous flow. Any inefficiency in tool production, labor rotation, or seasonal window utilization compresses the available margin. In other words, even when limestone throughput scales plausibly across thousands of workers, the slow cadence of granite tasks may strain the construction schedule to its theoretical limit. And so we arrive at the essential question: if granite is the bottleneck and the rest of the pyramid depends upon it, does the mathematics of tool wear, labor availability, transport, energy, and seasonal constraints allow the project to conclude comfortably within the 20 to 27-year reign traditionally attributed to Khufu? Or do the numbers suggest that completing the internal precision work of the pyramid approaches the edge of feasibility, demanding the maximum efficiency of every resource, human and material, across the decades-long enterprise? Granite is not forgiving. Unlike limestone, whose softness accommodates imprecision, granite demands exacting care. The King's Chamber and its associated internal structures demonstrate tolerances that are astonishing even by modern standards. Blocks sit with flatness deviations measured in millimeters across surfaces several meters wide. Mating surfaces align with such precision that, in some cases, gaps are imperceptible to the naked eye. Drill cores extracted from the blocks reveal striation patterns that indicate remarkably controlled movement, repetitive abrasion, and careful alignment. Spiral marks on certain holes suggest consistent rotational motion, either by tubular drilling or repeated pounding with an abrasive slurry. These are not embellishments or fanciful interpretations. They are measurable surface characteristics, catalogued and quantified by modern Egyptologists and experimental archaeologists. The core question arises naturally from these observations. Given the known tools, copper and bronze implements, dolerite pounders, and quartz sand as an abrasive, can the observed precision be achieved within the historically accepted timeline of 20 to 27 years? It is one thing to remove cubic meters of stone. It is another to achieve the flatness, alignment, and surface finish exhibited in the King's Chamber, the relieving chambers, and the portcullis systems. Each additional millimeter of tolerance requires extra cycles of abrasion, tool management, and worker attention. Errors accumulate. Each correction consumes energy, manpower, and time. Experimental replication provides insight. Modern tests using copper saws and abrasive sand on granite surfaces reveal removal rates that are slow and labor-intensive. Achieving a flat surface across a 2-meter block can take days of continuous work by multiple skilled operators. Drilling a single core with controlled rotational motion to produce a clean cylindrical cavity demands repeated passes and careful monitoring. Wear on the copper tool is rapid. Reshaping and recasting are frequent. Even with continuous labor, the throughput is limited. The mathematics become stark when scaled. The Great Pyramid's King's Chamber alone contains roughly 10 granite blocks weighing between 40 and 70 tons each. To achieve precise flatness and alignment on all surfaces of each block, workers would need to execute multiple cycles of cutting, grinding, and inspection. Adding drill cores for portcullis channels increases the labor further. Multiply these operations across all granite blocks in the pyramid, including relieving chambers and support beams, and the labor investment grows exponentially. Time is the ultimate constraint. If the project had 25 years, only a fraction of that duration could be devoted to granite shaping each year due to the seasonal rotation of labor, transport windows from Aswan, and the need to balance limestone production, ramp construction, and casing stone placement. Under the moderate assumptions of tool efficiency and human output previously calculated, completing the precision work appears to press against the upper bound of feasible schedules. even slight inefficiencies, a dull copper edge, an unexpectedly hard quartz inclusion, a delay in smelting copper replacement, cascade into significant schedule pressure. The surface characteristics provide a tangible measure of this challenge. Flatness tolerances, surface roughness, and drill striations are all evidence of not only labor and technique, but also time. Each striation represents a moment of labor applied. Each consistent spiral indicates controlled repetition. Collectively, they quantify the effort embedded in the stone. When experimental removal rates are applied, the required labor hours for observed precision often approach, or in some conservative calculations, exceed what could reasonably be delivered by available manpower and tool supply within the accepted range. This raises a subtle yet critical question. If abrasive sand cutting using copper tools can account for stone removal in theory, can it also account for the level of precision observed without extending the timeline? The margin is thin. Precision work consumes disproportionate attention compared to bulk removal, and the sequence of operations cannot easily overlap without risking damage to previously prepared surfaces. Each block's final dimensions are interdependent with others. Misalignment in one compromises the fit of subsequent stones, further emphasizing the labor intensity of precision. It is here that the cutting speed problem becomes acute. Granite is not merely a hard rock. It is a test of coordination, material science, and workflow management. Achieving the observed flatness, alignment, and drilled features without delays demands sustained, uninterrupted labor, a consistent supply of freshly forged copper tools, and careful attention to energy, food, and transportation logistics. Any disruption, from seasonal labor shortages to tool degradation, amplifies the time required, shrinking the margin for completing the entire granite program within 25 years. Measured surface characteristics also challenge assumptions about tool mechanics. Spiral drill marks suggest a continuous controlled motion, implying that workers had developed methods to translate rotational energy into cutting with consistent pressure, a technique that demands both skill and endurance. Flatness tolerances indicate repeated verification and fine grinding, likely with abrasive slurry applied in carefully measured strokes. Each incremental pass represents the intersection of labor, material, and energy, compounded over dozens of blocks. No mystical or alien explanation is required. The question is engineering, logistics, and material science. The physics of copper and granite, the measured labor output, the rate of tool wear, and the total energy available define the boundaries of what could be achieved. Within these constraints, the observed precision pushes against the maximum feasible throughput of the Old Kingdom workforce. And so the tension crystallizes. If the historical time frame is correct and the tools and techniques are as assumed, the labor and energy calculations suggest that the observed granite precision is at the limit of what is physically achievable. Every block completed represents the coordination of multiple systems operating near peak efficiency. There is no room for extended error, inefficiency, or downtime. This leads naturally to a pivotal question. If time is constrained, if labor, energy, and copper supply are finite, then the granite shaping methods observed must have been highly efficient, perhaps more so than simple models suggest. Were there techniques or optimizations lost to history that allowed workers to achieve this remarkable precision within the available window? Or does the arithmetic indicate that the traditionally accepted timeline required extraordinary, near-continuous effort, meticulous planning, and flawless execution beyond what modern replication experiments predict? The stone speaks. Its surface characteristics are not decoration or accident. They are a ledger of labor, energy, and time. They quantify what was possible and what strained the boundaries of technological capability. And if the cutting speed problem is defined as the discrepancy between measured labor and material removal versus the assumed construction window, then granite precision is the ultimate expression of that tension, demanding careful reconciliation between reality and possibility. Even within orthodox scholarship, There are ways to imagine efficiencies that might reconcile the apparent tension between granite precision and the historical time frame. The problem is not whether the Egyptians were capable of ingenuity, they clearly were, but whether that ingenuity, when expressed in the known tools, workforce, and energy constraints, is sufficient to meet the timeline. Several mechanisms emerge as potential accelerators, each grounded in plausible Old Kingdom practices. One obvious factor is scale of labor. Archaeologists debate workforce estimates widely, but some argue that seasonal laborers could have been higher than the conventional 20,000, or that more permanent staff could have been mobilized for granite-intensive operations. Increasing the number of skilled cutters and transporters directly reduces the labor burden per individual. If, instead of 10 workers on a single block, 20 operated in parallel, cutting time per block could be halved, at least in theory, yet manpower alone cannot solve all constraints. Human endurance is finite, and tool wear scales with the number of simultaneous workers. Each saw or drill still requires maintenance and resharpening. Doubling crews accelerates removal, but it also doubles copper consumption and energy expenditure, producing downstream stress in smelting, charcoal supply, and provisioning. Scale solves part of the problem, but creates new bottlenecks elsewhere in the system. Parallel cutting teams offer another possibility. Rather than one team finishing a block sequentially, multiple groups could work simultaneously on different faces. For slabs with multiple surfaces, one team might focus on top flatness while another works the sides, and a third applies final polishing. This approach is not hypothetical. Modern reconstruction experiments show that coordinated teams can indeed reduce total time per block. But synchronization is critical. Granite is unforgiving. A misaligned strike, uneven pressure, or rushed operation can create cracks or uneven surfaces, forcing rework. Parallelism is constrained by precision requirements. While it can reduce wall clock time, it cannot multiply efficiency indefinitely without risking damage. Pre-shaped quarry finishing is also a plausible method. Some evidence from Aswan suggests that blocks may have been roughly squared before transport. By removing irregularities at the quarry face, transport weight is slightly reduced and finishing on the plateau is less extensive. This reduces cumulative labor hours, but only partially. Transported blocks must still achieve tight tolerances, especially for mating surfaces and alignment within the king's chamber. Pre-shaping expedites overall flow, but cannot fully replace meticulous final work. Its contribution is incremental, not transformative. The length of the rain window is sometimes cited as a possible factor. If Khufu's effective construction period extended toward the upper end of 27 years, or if preliminary quarrying began slightly earlier, total time available increases. Even a few additional years reduce daily labor intensity and buffer against delays. However, historical and epigraphic evidence constrains flexibility. Quarry marks, cartouches, and later administrative records collectively support the majority consensus. The primary construction fell within Khufu's reign. Extending the period by more than a few years risks conflict with documented attributions. Marginal gains are possible, but cannot entirely resolve the cutting speed problem. Administrative efficiency is another variable. Coordinated provisioning of food, water, and tools allows laborers to work without interruption. Efficient scheduling of rotations, timely delivery of copper, and careful sequencing of transport cycles all reduce idle time. In the context of Old Kingdom bureaucracy, this is plausible. Evidence of extensive administrative organization, storage magazines, overseer records, and seasonal labor coordination supports the notion that management mitigated inefficiency. Yet even the most disciplined system cannot fully overcome physical limits. Granite must still be abraded, shaped, and transported within mechanical realities. Skill specialization offers further acceleration. Assigning dedicated crews to specific tasks, one team for flat surface finishing, another for drilling, another for transport, optimizes labor efficiency. Experience matters, More practiced workers expend less energy, make fewer errors, and maintain higher throughput. Ancient societies clearly valued apprenticeship and skill transmission, suggesting that crews were capable of sustained high-efficiency work. Nevertheless, specialization is bounded. Copper edge wear, charcoal supply, and fatigue impose non-negotiable limits on how fast blocks can be produced, regardless of proficiency. Testing these accelerators against the numbers reveals a nuanced picture. Doubling crews, pre-shaping blocks, and deploying parallel teams each reduce individual block labor by some fraction, perhaps 20 to 50% in optimistic calculations. Longer rain or administrative optimization adds additional buffer, yet none of these factors multiplies throughput enough to fully remove the tension highlighted by previous energy, labor, and precision calculations. At best, the combination narrows the gap, making the schedule plausible under tightly controlled, highly disciplined, and uninterrupted operation. But it does not entirely eliminate the strain on resources. The cumulative insight is subtle but important. The apparent contradiction may not indicate impossibility, only compression. The pyramid could have been built using orthodox methods, tools, and workforce, but only if every element of the system, labor allocation, tool supply, transport logistics, energy provisioning, and precision work, operated near the upper bound of efficiency. Small inefficiencies or unforeseen delays would cascade into significant schedule pressure, leaving little margin for error. Granite, the minority material in mass but maximum in labor intensity, dominates the critical path. Its requirements compress the rest of the operation, forcing high coordination for the broader limestone construction, transport, and administrative network to maintain continuous flow. This perspective reframes the problem. It is not that Old Kingdom technology or labor organization was inadequate. It is that the project existed at the edge of human and material capability. The Great Pyramid is a monument not merely of stone, but of optimized workflow, concentrated skill, and energy distribution managed with extraordinary precision. Granite's hardness and precision demands reveal the system's vulnerability. Any misalignment in supply chains, labor, or tools would threaten timely completion. In this sense, the cutting speed problem is less a question of impossibility than a question of how tightly compressed the entire project must have been to fit within a finite, historically plausible window. The lesson is both practical and humbling. The Egyptians did not cheat physics or invoke unknown methods. They maximized the potential of existing tools, labor structures, and energy resources. They coordinated hundreds of individuals, synchronized seasonal labor, and managed scarce materials with extraordinary foresight. Granite cutting emerges as the bottleneck not to highlight inadequacy, but to demonstrate the precision with which the system as a whole must have operated. And if compression defines the challenge, then the final question becomes unavoidable. How close did reality come to the theoretical limits suggested by our calculations? And what does that reveal about the ingenuity, organization, and sheer human determination required to move and shape stones of unparalleled hardness within a king's lifetime? The attribution of the Great Pyramid to Khufu is widely accepted, yet it is not beyond scholarly debate. Quarry marks discovered in the relieving chambers bear cartouches associated with Khufu, suggesting a direct link to his reign. These inscriptions, etched into the granite blocks, provide the primary historical anchor connecting the construction timeline to a specific pharaoh. Yet, even within Orthodox Egyptology, questions linger. The marks are not extensive, and their interpretation relies on careful contextual analysis. Some scholars argue that the cartouches may reflect later administrative oversight, or that preliminary quarrying could have begun before Khufu's formal reign. Others raise the possibility that certain blocks were finished after his death during subsequent projects in the same complex. Despite these debates, the evidence supporting Khufu-era construction remains compelling. The majority of archaeologists concur that the bulk of the pyramid, from the limestone core to the granite king's chamber, was assembled within his reign, roughly 23 to 27 years. Radiocarbon dating, combined with architectural typology and comparative studies of contemporary tombs and monuments, reinforces this attribution. Fringe theories, including suggestions of pre-Khufu foundations or later posthumous completion, lack substantive material evidence and are generally dismissed. While minor chronological adjustments are possible, they do not substantially alter the framework of construction, tool use, or labor dynamics. It is critical to recognize that any shift of a few years in the starting or ending point of construction does not significantly change the technological constraints. The toolkit, copper and bronze implements, dolerite pounders, abrasive sand, sledges, ramps, and human labor organized into rotational and permanent crews remains entirely within the capabilities of the Old Kingdom. There is no introduction of unknown alloys, advanced machines, or supernatural methods. The physics and material science of granite, copper, and human effort are immutable, independent of which ruler presided over the project. Whether granite was cut at the very start of Khufu's reign, or during the final years of his predecessors, the cutting speed problem persists. This perspective frames the debate in practical terms. A marginal shift in attribution may alter the starting year by a handful of months, or even a couple of years, but it does not alleviate the arithmetic of labor, energy, tool wear, and precision required to complete the granite blocks. If a block requires 100 worker-days to shape and copper saws wear at predictable rates, the total man-hours do not disappear because the cartouche is scratched a year earlier. The underlying constraint remains the intersection of material hardness, tool efficiency, and the temporal window available for sustained work. Moreover, the granite itself, quarried at Aswan, presents identical challenges regardless of attribution. Transport, handling, and precise finishing are governed by physical realities. Even with a longer reign, seasonal labor rotations, energy availability, and administrative logistics continue to define the system's ceiling. The technological and operational framework is consistent with the Old Kingdom toolkit. What varies is the historical narrative attached to the pharaoh. Granite cutting, therefore, is a timeless test of capability within the context of the period, not a variable contingent upon political attribution. Reassessing Khufu's reign also intersects with broader project planning. Any minor extension of the timeline, perhaps a 2-year earlier start or a similar delay, provides marginal breathing room, but it does not resolve the cumulative pressures. Tool production, smelting, fuel provisioning, transport, labor scheduling, and finishing precision are all bottlenecks that scale with the granite workload. Small temporal adjustments reduce stress, but cannot fully eliminate the cutting speed problem. They merely shift the point at which maximal efficiency must be maintained. This leads to a broader reflection on archaeological interpretation. Material evidence, cartouches, quarry marks, and architectural analysis anchors the narrative in history, but the engineering problem exists independently. Scholars can debate the precise year, the seasonal scheduling, or the attribution of individual blocks, yet the physical laws governing granite hardness, copper wear, and human labor remain unchanged. The Great Pyramid is simultaneously a historical artifact and an engineering case study. Its construction cannot be fully separated from either domain, but the measured challenges transcend the specific pharaoh credited. In this context, the Khufu attribution serves as both a historical guidepost and a temporal constraint. It delineates the window in which ancient builders must have completed a project of unprecedented scale, with the known materials and labor organization of the period. Even accounting for minor disputes over cartouche interpretation or possible early preliminary work, the essential engineering reality is unchanged. Granite cutting, transport, and placement represent a concentrated test of Old Kingdom capabilities. The timeline, workforce, and toolkit collectively define what was possible. Historical attribution merely situates that possibility in chronological terms. Thus, even under rigorous reassessment, the cutting speed problem survives. Shifts in attribution do not erase granite's hardness, copper's limitations, or the finite energy available to laborers. They do not change the arithmetic of tool wear, human metabolic output, or the logistical coordination required to move multi-ton blocks over hundreds of kilometers. The system remains constrained. The Old Kingdom toolkit, combined with measured labor and energy, sets a ceiling for throughput, independent of minor chronological adjustments. When viewed in this light, the Great Pyramid emerges as an extraordinary testament not to myth or legend, but to precise coordination, advanced project management, and the full mobilization of available materials and human effort. Khufu's name anchors the narrative, but the engineering challenge transcends individual rulers. Granite blocks, copper saws and sledges impose immutable limits. Within those limits, the project succeeded, but only with exceptional discipline and organization. The audit is clear. Historical attribution may shift slightly. Scholarly debate may nuance the timeline, but the measurable facts remain. Granite's hardness, tool wear, labor hours, energy consumption, and precision requirements are fixed realities. The cutting speed problem, far from hypothetical, persists under scrutiny. The scale, coordination, and precision required are undeniable, leaving the fundamental tension intact. And so the question becomes unavoidable. If attribution, timeline, and methodology are reconciled within orthodox scholarship, what survives the audit? What portion of the project is comfortably explained, and what portion presses against the very limits of Old Kingdom capability, forcing us to reckon with the exceptional coordination, labor discipline, and technical mastery required to realize a structure of such enduring precision and scale? The audit begins with granite itself. Roughly 8,000 tons of the hardest stone known to the builders were quarried from Aswan, transported over 800 kilometers, and precisely fitted into the heart of the Great Pyramid. Each block, averaging 40 to 70 tons for the King's Chamber and relief structures, demanded multiple cycles of cutting, drilling, finishing, and alignment. Experimental replication suggests removal rates ranging from a few cubic centimeters per hour on the conservative end to more generous rates under optimistic assumptions. Multiply these by the total granite volume, and the cumulative labor requirement emerges. Hundreds of thousands of man-days, distributed across skilled teams and seasonal labor rotations. Tool production forms the second ledger. Copper saws, tubular drills, and dolerite pounding implements wear rapidly when applied to quartz-rich granite. Estimates of copper loss per hour, combined with required reshaping and recasting, indicate that tens of tons of metal had to be smelted, maintained, and supplied continuously. Fuel consumption for annealing, the labor for forging and maintenance, and the administrative coordination of smelting cycles all impose a further layer of constraint. Tools are not mere instruments. They are consumables that structure the flow of work. Transport adds its own measure. Granite blocks, sledged over desert sands or floated along the Nile, required repeated handling. A single 50-ton block involves loading, river transport during seasonal flood windows, offloading, hauling to the plateau, and precise positioning. Each step consumes labor, energy, and time. Friction, slope, and load-bearing considerations dictate throughput limits. Even when transport runs efficiently, the rhythm is dictated by granite precision and seasonal opportunity. Labor, energy, and food complete the audit. Metabolic output, caloric intake, and workforce distribution define the ceiling of sustained work. Seasonal rotations, permanent crews, and specialized skill sets must all align. Under optimistic assumptions, high tool efficiency, coordinated teams, smooth transport, and minimal downtime, granite cutting and placement could occupy a fraction of the workforce without overtaxing other operations. Under moderate assumptions, labor allocation is tighter, but the schedule remains feasible. Under conservative assumptions, with slower removal rates and tool wear factored fully, the timeline compresses, and the system operates at the edge of human endurance and logistical capacity. Three conclusions emerge from these calculations. First, Under idealized but plausible conditions, the 23 to 27-year construction window comfortably accommodates granite cutting, transport, and placement. The numbers balance. Labor, energy, and materials can meet the demand. Second, under moderate but realistic assumptions, slight inefficiencies, slower removal rates, minor interruptions, the timeline barely fits. Success requires near-optimal coordination, sustained labor, and minimal downtime. Third, under conservative estimates, lower cutting speeds, high tool wear, and modest labor disruptions, the timeline strains, approaching or exceeding plausible bounds. The margin for error vanishes. Even minor deviations could delay completion. These outcomes are not speculative. They are derived from measurable facts: hardness of granite, copper tool capabilities, experimental removal rates, energy requirements, transport logistics, and workforce dynamics. Each factor can be quantified, modeled, and tested against historical and archaeological evidence. The Great Pyramid does not defy arithmetic, it confronts it. In this synthesis, one truth stands out. The monument is not mysterious. Its scale, its precision, its endurance across millennia, all are extraordinary, but they are measurable. Granite, labor, copper, food, and energy form a ledger that, when tallied, defines what was required, what was feasible, and what pressed the limits of human capability. Myths, speculation, or wonder add context, but they do not alter the arithmetic. And when measured, the pyramid forces a more unsettling reflection, not on the identities of its builders, not on legends or divine inspiration, but on our own assumptions about capability. How often do we underestimate the intersection of material limits, human coordination, and temporal pressure? How often do we presume that historical feats are inexplicable, when in fact they are simply extreme exercises in optimization, discipline, and ingenuity? The Great Pyramid endures because its construction obeyed physics, labor dynamics, and material science. Granite cutting demanded extraordinary coordination. Tool production required continual attention. Transport and energy imposed finite limits, and yet the builders achieved it, not by transcending these constraints, but by mastering them. So the question lingers as the final measure. When we quantify, calculate, and confront the numbers, we are left with the reality that greatness is not always miraculous. Sometimes it is merely astonishingly, precisely engineered. And in that measurement lies a deeper challenge, not to marvel at mystery, but to reckon with the magnitude of what humans were capable of, and to ask whether our own estimates of possibility remain too conservative, too cautious, too timid in imagining what disciplined, measured effort can achieve. The pyramid is not mysterious, it is measurable. And when measured, it forces us to confront a question far more unsettling than myth. Not who built it, but whether we have underestimated or miscalculated what was physically required. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.